We will now go over what we learned in course section 4 to describe how to model behavior of benzene and volatilization using Matlab software. Mass transfer from a liquid control volume to a gas control volume via the process of volatilization can be modeled as determined in the previous course video. The relationship between the two control volumes in the two-resistance model for the benzene-contaminated water source has been seen here, where the transfer rate across the two films is limited by the liquid film mass transfer rate. As explained before, this deems the model a single resistance model for mass transfer. The mathematical derivation of the mass change across the two films describe an inverse relationship between the two flows, with the flow of mass into the gas control volume being directly tied to the rate that it can cross the liquid film. This is due to the mass transfer rate for the gas film being very large in magnitude compared to the mass transfer of the liquid film. The liquid concentration of benzene at the interface is not known, but we substituted the concentration for the gas concentration of benzene at the interface divided by the Henry's law constant, which is in turn equal to the bulk concentration of the gas control volume. This bulk concentration is known and is able to be substituted due to the large Kg value, indicating that there is not a difference between the benzene concentration in the gas control volume and at the gas interface. To model the behavior of this mathematical model digitally, we'll be using Matlab software, and to get the most out of the software, we'll be looking at both analytical methods as well as numerical methods of modeling. This will give us multiple tools that will be useful in problem solving. Using an analytic approach, we will be able to derive interfacial mass transfer constants or create a range of values for concentrations in different control volumes depending on what information we have at our disposal. To find behavior of a model using only known constants, two key tools at our disposal for this portion of the coding process are the sims and Dsolv commands. Sims will allow us to describe placeholder values as variables in a potential equation that we want our code to use as a model of behavior. Dsolv will take the products we get from the sims coding and use them to produce useful models of the interfacial mass transfer over a given time. The first step in using the sims tool is to describe our known variables at the beginning of a new script. As seen here, we have described our known variables at the beginning of our new script. This is done simply by determining an appropriate name for our variable, such as KL for the liquid film mass transfer rate, and setting it equal to a value we are given. For the sake of instructional simplicity, we have used placeholder values in this instance. The sims line itself will be written similarly to what you can see here. Variables necessary for the derivation will be listed after sims and will appear as pink text. In this case, the variables chosen are the dependent variables for the concentration in water and air control volumes. It is important to keep the variable names in our sims code distinct from the names of the variables that are attached to real values, as using the same variable name in both instances can lead to coding errors when we try to run the script. Once we have added all the variables we need to establish in the sims line, we can start defining our ordinary differential equations. These can be written as seen, though it is important to note that both the sims line, these two new lines, and many others you will see in this course may be structured slightly differently and still achieve adequate results. The ODEs will be described by setting the visible double equal sign to our derived equations for each of the interfacial mass transfer rates. The ODEs are both being solved in this example at the same time, so as to accommodate this in our code, we will make a 1x2 matrix containing both ODE variable names and setting it equal to a new variable. This will allow the Dsolv to later use this single variable to solve for both ODEs at the same time. We will next need to set our conditions. In this particular case, our only conditions are our starting values for concentration, which are both known. As with the ODEs, the initial concentration variables will be placed in a 1x2 matrix so that they may be referenced by a single variable in the Dsolv script later. This concludes the script necessary to set up the use of the Dsolv command, though it is important to note that while we are using the example of two specific derivations, those being for the interfacial mass transfer of benzene from one control volume to another. This process can be repeated for any known ODE that you need to model, provided you have enough known values to allow your ODE to function over time. The next line of code will call for the use of the described ODEs in the Sims portion of the code and set their solution values equal to two placeholder variables labeled as functions of time. This is where Dsolv will call those values from the two condition and ODE matrices. The next line after that simply describes a time domain, with the first value being the initial time, the second value being the time step between each use of our ODE derivations, and the last value is the amount of time we want our model to simulate the interfacial mass transfer. To view our model, we need to plot it. We could simply leave it as is and call for specific values of our script at a specific time, but that only gives us one data point to evaluate. To plot our ODEs over our time domain, you will describe the x values for the plot as the time variable, which will let Matlab know that this is the range of values we want on the x-axis of our plot. The y values must be calculated by our script. To enact this, use the double command, and inside the command, reference the variable for each of the two ODEs we described as being a result of our Dsolv script, and place the variable for the time vector we created in place of the placeholder t that was there before. This tells our script that we not only want to plot y values, but that they should use our Dsolv code on each of the time steps in our time vector to create those new y values. The hold on code will enable our plot to place both y value ranges on the same plot for each of our two ODE functions. The title, y label, and x label commands are self-explanatory, and there is not much room for deviation here. When using this script skeleton for other purposes, change the writing inside of the apostrophes to change the labels of these axes. The legend of each of our y value ranges are described in the order they are plotted above, so make sure that the order they are labeled in the legend command is the same, or the plot will describe the wrong values for the wrong concentrations. The location and best commands simply tell Matlab to place the legend in the spot on the plot that will be the least inhibitive to the viewer. Hold off will ensure that the plots used in later portions of our script do not get placed on our analytical solution. The resulting plot seen here is a good example of what your code should produce. Another invaluable tool that can be used when information is limited is the fit function. This tool will allow a user to find constants that were not given using only some data points and a general understanding of the ODE structure driving the reaction taking place. There are several ways to structure this script, but generally you will set a placeholder variable equal to the fit type described by the ODE structure with unknown constants, and the independent and dependent variables labeled. The second line will describe the way we want the fit function to operate later, and in this example, a nonlinear least square regression was used. Start points should also be described, though these tend to be arbitrary small values that should not dramatically impact the constants derived from the fit function. The fit function line will then be structured as seen, allowing constants to be called from their index within the resulting variable of our fit function script. There should be all the instruction necessary to either use Matlab to directly model the interfacial mass transfer we discussed in course video 4, or to analytically model behavior of another ODE with known or unknown values or relationships. Moving on to a numerical method of modeling the benzene volatilization, we'll be first focusing on the ideology behind the script we'll be writing. This numerical method is based on Euler's method. The Euler method allows us to use known values at a given time and a known ODE for a relationship to model behavior without knowing the actual equation the derived ODE was based on. This is extremely useful. As described above, we can find the k constants for ODE relationships using our Matlab script. This means that once we establish how to properly use this numerical method, we can use very little information to adequately predict the behavior of a physical interaction. The basic form the method takes is as seen, where a new y value is set equal to the old y value plus the product of the change in time, or the time step, and the ODE value for the old Y value and old time value. Using this basic structure across a large time domain with a small time step size will produce a model that is close in approximation to the analytical and true behavior of a process. This is because the ODE is the change rate for a change in time, and we are using sufficiently small time steps that the error that would otherwise be introduced by this method is so small as to be negligible in most instances. To create a script that does not require us to code each and every single time step calculation individually, we will need to use a new tool. This new tool is referred to as a for loop. A for loop uses a set of described conditions and will perform the actions required between the beginning and the end of the for loop until those conditions are considered true. In this case, we will need to initialize some variables to use our loop as seen at the top. We know how long we want our time domain to be, and we know to make our time steps small, so we will make a time vector using the same way as described in the Dsolv script, but this time we will also create a placeholder variable that is equal to the number of steps our loop will function. This number is simply the total time divided by the time step. The vectors for our two concentrations also need to be initialized. However, these will simply be zero vectors equal in size to the number of time steps we will run our for loop. The initial values for our first y values will be initialized, and these will be referenced in the for loop, so they may be placed in the vector of y values the for loop is going to make for us. The beginning of the for loop will then be structured as seen, where a placeholder variable is initially equal to 1 and will progress in increments of 1 until it is equal to the total number of time steps. It is important to note that the same rules as described for the Dsolv and Sims script apply here, in that you will need to use different variables inside the for loop than the ones you use to describe your desired y values. This is necessary to avoid script errors when we run the code. The next two lines will describe the ith value in our y value vector as the same as our placeholder variable for our initial y value concentrations. The ith value during the first for loop will then become the first value of the vector. In the two new lines, we will apply our knowledge of the Euler method to start creating new model predictions within our y value vector of concentrations for both sides of our interface. The structure here is the same as described earlier, where the new y value for the next time value will be the old y value added to the product of our time step multiplied by the OD value for our old y and time values. The end of our for loop must describe the new current y value as the same variable the first portion of the loop is using to place y values into successive vector indexes. This is necessary because without this step, the loop would continue to place the initial y value into every index of our resulting vectors. Now that we have added these last two lines, every new y value will be placed in the next space in our resulting y vectors for each of the two models. This loop is now complete, and if it is coded properly, it will run until the initial condition is met and produce a range of concentrations closely resembling the true behavior of our single resistance model for a given domain of time values. Here, the commands for plotting our vectors are very similar, with the only notable differences being that we aren't telling our plot to call the earlier script to calculate our y values as they are plotted. An important note here is that both of our y value vectors must be produced from the same for loop so that they are changing across the same time steps. This is because the change in concentration at each time step on both sides of the interface are going to change the behavior of the mass transfer. So if only one is simulated at a time, the results will not represent the physical process as necessary. With that, you should have all the tools necessary to both analytically and numerically model the behavior of the volatilization of benzene from a non-flowing open surface water volume, as well as any other ODE you have sufficient information to simulate. These are the provided sources that were used to derive this course section.